Alright, so here we got question 5 of the AP Calc AB portion. For your for your response, this is no calculator right here. Alright, consider the curve defined by the given equation. Um, that's a implicit equation. Y is not explicitly solved for, so we have implicit equation right there. And it can be shown that dy dx is given there. Okay, so we have an equation here, and its differential equation. There is a point on the curve near 2, 4 with x-coordinate 3. Use the line tangent to the curve at 2, 4 to approximate the y-coordinate at this point. Okay, so when I see this right here, I see line tangent at this point. And if I see line tangent, I'm just going to be thinking this right here. I'm going to write down an expression that comes to mind. Y minus y1 equal to m times by x minus x1. There is your tangent line. We can start filling this in already too. So we have y minus y1, which would be 4, because that's our given y-coordinate, equal to m times by x minus 2. And because 2 is our given x-coordinate. Now I need to find m. I know that m represents slope, and another word for slope would be derivative. And an expression for our derivative is given to us. So m is equal to dy dx. We'll say this right here. At 2 comma 4. So that way we can just go ahead and plug it in. So negative 2 times by 2 divided by 3 plus 4 times by 4. So we got negative 4 on top. We got 3 plus 16 here. So we got negative 4 over 19 as our slope. So this is the slope of our tangent line at this point on the curve. Okay, so if I go ahead and plug that back into my approximation here, I'm also going to add 4 to this side over here. So I get y is equal to negative 4 over 19 times by x minus 2 plus 4. So here's my tangent line, and I'm supposed to use my tangent line to approximate the y-coordinate at x equals 3. So I'm going to approximate y by plugging in x equals 3. Okay, so y is going to be equal to negative 4 over 19. If I plug in 3 here, I get 3 minus 2, which is just going to be 1. So in any case, I get y is approximately equal to negative 4 over 9 plus 4. And that should be a good enough answer. This is non-calculator, so I could go ahead, put this over 1, get a common denominator right there, and do some arithmetic right here if I wanted to. But you also run the risk of simplifying incorrectly, which will lose you your point. So this right here, we'll call that good right there. And that should get you all the points for part A. Okay, moving on to part B. So is the horizontal line y equals 1 tangent to the curve? So this curve that we have right here, we don't really, I don't really know what it might look like, but whatever it looks like, it's saying, so say that we have our graph right here, we have the line, tangent line y equals 1. So whatever this curve might look like, does it have a horizontal tangent here? Again, I don't really know what's happening for the curve, but is the curve, whatever it might look like, is the line y equals 1 going to be tangent to it? So there's probably a couple different ways you can look at this right here, but I'm going to try and think about it in the most calculus kind of a way that you can. So a horizontal, let's say this, a horizontal tangent would be when dy dx is equal to 0. Correct, right? So that's whenever the slope of the line is 0. So that's when it would occur. So if you think about that, well, 2x over 3 plus 4 y would have to be equal to 0, right? Okay. Man, I'm trying to think of too many ways of doing this. Um, the only way that this could be 0 is if our numerator is equal to 0, and that could only happen if x is equal to 0. So, if that's the case, you could plug 0 in for x here, and solve for y. You would have to get 1 out of it in order to confirm that. I don't think that's going to work right there, though. Let's also think about it this way. I'm going to come back to this right here. So at y equals 1, so let's go ahead and plug in y equals 1 here and see what we get for x. And if it doesn't equal 0, then we know that we know that we don't have that the horizontal line at y equals 1 is not tangent to the curve, right? So I've identified that x has to be equal to 0 for this to be equal to 0. Okay, so let's say I plug in 1 for y, right? So if I plug in 1 for y, I get x squared plus 3 plus 2 equal to 48, and therefore I get x squared is equal to 43, and I get x is equal to plus or minus the square root of 43. Okay, so if I were to, so I have a coordinate point. I have y equals 1, and I have x is equal to plus or minus the square root of 43. So if I plug that into my dy dx, I need to get 0 for it to be a horizontal tangent, right? Okay, so you can already tell it's not going to work that way. So negative 2 times by, even if plus or minus the square root of 43, right? Over 3 plus 4 times by 1, 1 because that's where the y would be, and this right here would be equal to negative 2 times by plus or minus square root of 43, either one, divided by 7. Either way, this is not going to be equal to 0. So we don't get a slope of 0 when we plug in the coordinate that we have for y equals 1 and x equals that. So yeah, so it doesn't equal 0. So I would just say that there is let's see here. So because dy dx does not equal 0 when y equals 1, I guess you can say, and x is equal to plus or minus square root of 43, because that's the coordinate. This is the corresponding x coordinate when y is equal to 1. Um, uh, th the horizontal line y equals 1 is not tangent to the curve. So I think that would be sufficient to get all the points right there. Again, there's definitely different ways to go about this. There could be one or two other ways that you can think about this right here. So yeah, I think that's just one of them. Okay. If you have another one, just let me know a different way that you guys think we can do this. If there's an easier way too, but that's just how I thought about it. Okay. Let's move on. So the curve intersects the positive x-axis at the point negative square root of 48, 0. So the curve intersects the positive x-axis. Okay, so if we were thinking about this as our graph right here, the curve intersects at a point over here that's okay. is the line tangent to the curve at this point vertical? So basically, it's asking, so if the curve right here, it's asking if this point right here, if the line is tangent. So very similar to part B, right? Only in this case right here, you would say dy dx, let's say here, vertical tangent, I'll just say this, occur when dy dx is undefined. So horizontal tangents would occur when dy dx is equal to 0, but in this case this would be and it's undefined. Now this expression right here would be undefined when the denominator is equal to 0, because we cannot divide by 0. So we're given a point, yeah? So we can test this point right here. So dy dx for the coordinate point we have here, so square root of 48 comma 0. So if we test this point into our derivative, we get negative 2 times by the square root of 48 and divide that by 3 plus 4 times by 0, which would be just negative 2 square root of 48 divided by 3. So obviously, right here we can tell that the derivative is defined at this coordinate point. So therefore, the tangent of the curve at this point is not vertical. So um, okay, so no, the line tangent at square root of 48 comma 0 is not vertical because dy dx is defined. And I guess you can say is negative 2 square root of 48 over 3, although that's not answering the question, but just saying that this is the value of the slope at that point. It's not undefined, so it is defined there, and this is the value. There you go, and I think that should get you your points there. That's one way of answering it. Okay, question 5. Let's see what we have here. So for t is greater than or equal to 0, a particle is moving along another curve defined by the equation given there. At the instant the particle is at 4,2, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. At that instant, what is the rate of change of the x-coordinate of the particle's position with respect to time? Okay, let me read through this one more time, kind of process the information. So at this point along this curve right here, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. So it's saying here, it's saying dy dt. So the rate at which y is changing with respect to time is equal to negative 2 units per second. So the y-coordinates, the y-coordinate of the particle's position is decreasing. Okay, and at that instant, what is the rate of change of the x-coordinate? So we want to find dx dt. It's asking us to find the rate of change of the x-coordinate particle's position with respect to time. That's dx dt. So what is that equal to? So we're going to use, it sounds like we're going to use this equation right here. We're going to use implicit differentiation and solve for dx dt, and we have x and y. Now, this a lot of the times implicit differentiation can be very difficult for students because you need to understand that each variable, so y, we're taking the derivative of y with respect to t, not x or y. We're not, and so same with x. We're not taking the derivative of any of these variables with respect to x or y. We're taking the derivative of all these variables with respect to t. So the chain rule will apply to each variable we take the derivative of. So for example, we take the derivative of y cubed, that would be 3y squared, apply the chain rule. So that would be the derivative of y. So we're going to call that dy dt, because we're taking the derivative of it with respect to t. Plus, now this part right here is also a little tricky because we have to use the product rule because we're taking the derivative of x and y with respect to t, and they're both defined in terms of t. So we'll do the first times by the derivative of the second, so that's going to be dy dt, and then so plus the derivative of the second, that would be 2, but now we'll say dx dt, we're taking the derivative of x with respect to t, times by the second. Let me make sure that I have that right. So the first times the derivative of the second plus the derivative of the first, which would be 2 dx dt, times by the second. And that will be equal to 0. This is a constant. Make sure whenever you take the derivatives of constants that they are 0. Okay, and okay, we have everything to plug in, so we know that y is going to be equal to 2 squared. dy dt is negative 2. That's given right here. Plus 2 times by 4. Again, dy dt is negative 2. Plus 2 times by dx dt. Well, that's what we're trying to find. Dx dt. And then times by y, which is 2. Did I plug everything in right? So y is 2. Y is 2. X is 4. dy dt is negative 2. Dy dt is negative 2. Okay, so let's go ahead and put these together. So 3 times by 4, that's going to be 12 times by negative 2, so that's going to be negative 24. And then 2 times by 4, 8, so that's going to be minus 16. Plus 4 dx dt, it's going to be equal to 0. We're going to add those to the other side. So that's going to be 4 dx dt, and that's going to be equal to, that should be positive 40. Yep. Divide by 4, so we get dx dt is equal to positive 4. We can say units per second. So what is the rate of change of the x-coordinate of the particle's position with respect to time? Sorry, I'm so bad at that should be 10, sorry. 40 divided by 4 is going to be 10, so 10 units per second. And that should be everything you need for that one. Okay?